Can you see it now?
Yes.
Okay, so thank you very much. Let's see what we can do with this project. So I think it was a good start. We learned all the methods. Now I'll give you some problems that I would like to solve. I hope these methods can be useful here. So most of what I will say is, well, most of what I will say is completely review, but some of it is related to the work we did recently here at EPFL and with Shot at CERN and now Xiang, and Noé, who are in Paris now. So I will be very brief in the motivation, because otherwise I cannot explain what the models are. So the motivation in the end is always about quantum gravity, so about trying to find UV complete, so consistent quantum mechanical systems that in some limit reduce to gravitational physics, to general relativity if you want. And so we use string theory. So in string theory, we have some examples of models like that. And what happens is that whenever we obtain, say, a classical limit, so that you obtain GR, so some classical limit of quantum gravity, on the side of quantum mechanical system, this becomes a many-body strongly interacting system. Okay? So that's why we need the help of Giuseppe to solve these ones to understand quantum gravity. So that's my motivation. So now I will give you, in increasing degree of interest and complexity, some models that appear in string theory that have quantum gravity, or that are conjectured to give quantum gravity, and in particular have limits that describe classical gravity. Okay, so the first one, which is really directly related to what Giuseppe was telling us about, is quantum mechanics. So we will have Hamiltonians. The only special thing about them is that these Hamiltonians are nicely written if we organize the degrees of freedom in matrices. Okay, so that's why it's called matrix quantum mechanics. So for example, let's start with bosonic models. So then X is some n by n matrix. So I will consider always Hermitian matrix. And so say the simplest model, which even I can solve, is just p squared plus x squared. Okay. So of course, X here, I will always expand it, or you can expand it, and it's useful to do it in terms of n square bosons, which are no longer matrices, where these TA are just the UN generators. Okay? So n by n matrices. And so if you normalize that, I will use this normalization, then these are just, right? This is just n square decoupled, right? Decoupled harmonic oscillators. Okay, so this is easy. So, but maybe I'll do it just once. So for example, for n equals 2, X will look like, so I did this carefully so that you have the right normalizations, something like that. X3 plus I X4, X3 minus I X4, okay? So you encode 4 normal bosons into a 2 by 2 matrix, and that's what you do. Huh? And the only other thing I need to say is that this P is also a matrix, right? So you also expand the matrix in PATA, and now PA, or if you want X, A, PB, commutes to I, right? So H bar equal 1. Sorry, I delta V. Okay, so that's just to set up notation. We organize degrees of freedom in matrices. Now, of course, the interesting thing is to make them interact. So we can, for example, write now a matrix, which is an Hamiltonian, which is p squared plus x squared plus a gx to the fourth, right? So now there's a quartic term, so now they are coupled. It's already a hard problem, especially if n is large, it gets harder and harder, right? So now these are n square coupled oscillators, okay? And okay, if you allow for more matrices, so let me just write this one, which is closer to what we will see next. So for example, if you have two matrices, then a very nice model that is worth start to think about is one where the interaction is a commutator. Okay, so this model actually has a discrete spectrum, although that's not obvious, right? Because commuting matrices don't see any potential. The potential is only for sorry, what am I saying? Sorry, I meant even if you remove these guys, so this part can be here or not. Even if you remove the mass term, right, the quadratic term, this interaction makes the spectrum discrete, although that's not obvious because you have valleys that do not see any potential, okay? So please interrupt if you have any questions, because I'm really trying to go step by step and be pedagogical, so it does not make sense if I'm not and something is not clear, okay? So please interrupt if something is not clear. Okay, so my comment is that discrete spectrum not obvious. You can try to convince yourself of that. It's an interesting exercise. Okay, so bosons, this is the kind of things you can study, but it turns out that in all models that we get in string theory, you also have fermions. So we have to introduce fermions. And the fermions that we see more naturally are Majorana fermions. So these are real fermions. Okay, so you have some number of them, different depending on the model. Okay, so this is some number of fermions. And the basic thing here is that for every pair of Majorana fermions, you can form the usual creation annihilation operators, right? So you take psi1 plus I psi2 and psi1 minus I psi2, and then C and C dagger and T commute to 1. And then you can do the usual thing that the vacuum is annihilated by C, and then C dagger on the vacuum creates a state 1, and then it stops, right? C dagger on 1 stops. So therefore you have two states. It's like a spin a half, two states for every pair of Majorana fermions. Okay, so that's it. But of course we will have many. So we will put them in n by n matrices. So the simplest model that I will tell you that also involves bosons and fermions is what's sometimes called the minimal BMN model. So it has two matrices made of bosons and two matrices made of fermions. So here, so each one of these matrices, again, you should expand, or you can expand in UN generators. And so alpha here is 1 or 2. And so the dimension of the, well, let me write it like that. The fermionic Hilbert space is 2 to the n squared. Okay. So of course you already guess that what's going to be interesting is the large n limit, and that's why this is a hard problem, because all these Hilbert spaces go very high dimension. You have many degrees of freedom.
Joao, sorry, can I interrupt just to set the bar very low? Can I ask a stupid question about the previous slide? So I'm sure I should know this, but so these psi's, the Majorana fermions are not, you're not going to represent them as Grassmann variables. I mean, I'm referring to
here.
that
I'm really
square is
talking
one.
about operators in the Hilbert space. It's really just quantum mechanics at this point.
Okay, so because I'm just because psi square is one, so these things do not anti-commute.
Psi square is one, yes.
Yeah, okay, thank you.
Yeah. Okay, so then let me tell you this Hamiltonian. So this Hamiltonian has these two bosons. So it has the two kinetic terms for the bosons. It also has this oscillator part, which I mean, I chose to units where this is set to 1. Then there is this commutator squared, okay, this quartic term. And now there's this fermions. So, okay, I'll write it and then I'll explain better what these numbers mean. Okay, so there's a bit long, but it's very explicit. So what I'm saying here, so this matrix is a fixed matrices. This is also, so these are like gamma matrices, but in this case, actually it's very explicit. So I will say gamma 1 is just the third poly minus the first, and gamma 2 is the first poly matrix. And this is just the product, gamma 1 times gamma 2, which is actually minus I sigma 2. Okay, so these are just some poly matrices. Of course, here there's a sum I from 1 to 2. Sometimes I don't write sums if the index is repeated. Okay. So you see, this is just quadratic in the fermions. So this would be just a fermionic oscillator, free. But here you have an interaction. So it's quadratic in the fermions, and there is the boson. Okay? So it's kind of Yukawa-like interaction. And there's also a quartic interaction. Okay? And in general, you could put different couplings, but if you put here G and here G squared, then there is some special thing in this model, it's supersymmetric. Okay? So that's why we like especially this model. In particular, the ground state has exactly zero energy. We know the ground state exactly. We don't know the ground state, we know the energy of the ground state. Computing the ground state is already the first challenge to Giuseppe. What is the exact ground state of large n of this model at large n? Like, can we compute observables in this ground state? What other things can I say about this? So of course, G equals 0 is decoupled harmonic oscillators. So the important thing is the symmetry. So this is going to be always the same. There's a symmetry which is just SUN. So that follows from the fact that we organize the model, the degrees of freedom into matrices. So you can just take some X or psi, both of them, and rotate it, conjugate it with a fixed unitary matrix U, right? So if you do that, the Hamiltonian is invariant because it's a trace of product of matrices. So UN is always a symmetry of these models. And in the string theory languages, sometimes we call this gauge symmetry, although in this quantum mechanical context, calling this gauge symmetry is just equivalent to saying that we are only interested in the invariant states under this symmetry, okay? Only on the singlet states under this global symmetry SUN. And then in this model, on top of this, there's an SO2 symmetry that just rotates x1, x2 as a vector, okay? So x1, x2 as a vector as like charge 1, you can make x1 plus ix2 as charge 1, x1 minus x2 as charge minus 1, and psi as charge 1 and 1/2 and minus 1/2. Okay, so this model, we actually already have some data. So it's a toy model sufficiently simple that we already had some data. In our paper, we studied with the Hamiltonian truncation. So we have some plots of the energy spectrum, but only for n equals 2. Okay, so we did Hamiltonian truncation, which is a method where we take the Hilbert space of the G equals 0 theory, take the first, I don't know, k excited states, and then in that space, we compute the full Hamiltonian matrix. It becomes a finite matrix, and we diagonalize the finite matrix. Then we try to increase k, but of course, this is difficult because of, well, very big matrices don't fit in the computer. And the problem is that as n increases, you need the size of the Hilbert space exponentially large. So this method is not good to go to IN. Okay, so this is the first model where I think would be interesting to test some of the ideas that Giuseppe was explaining. Okay, so this is about toy models.
Sorry, Joao, and the bosonic model, did you have data for that, or
Sorry?
the pure bosonic case, is it interesting enough to be solved, or?
The pure bosonic case, I think it's more for warm up, yeah, when you're setting up the thing. There is also data because when we did this one, we also warmed up with the bosonic, and there are other papers that that worked on it, yes. Sorry, can you just tell me, did I start at 40 exactly, or otherwise I need to hurry up?
You started at 45.
Okay, so I'm kind of halfway. Okay, good. So now that we warmed up, now I can tell you the real deal. So the real models that we care about, that we would really like to solve, have these names. I will not even explain what the names are. Doesn't matter. I will just write the Hamiltonians so that we all know what these models are. So the first point is that they have more matrices. Okay, they have 9 bosonic matrices and 16 fermionic. Okay? So we see that even when n is 2, which is the simplest thing, 2 by 2, if n is 1, all these models will just become free oscillators. So n equals 1 is too trivial. N equals 2 is the most, is the simplest. Already has many degrees of freedom because it starts with, these numbers are fixed. They are not a parameter. So for example, the dimension of the fermionic Hilbert space, right, which is finite dimensional, is again 2 to the 8n squared. Now we have this 8 because we start with 16 Fermi. Okay. So what are the Hamiltonians? So let me quickly write them. So now I introduced all the language, so it will be clear. So there is this pi square where I goes from 1 to 9, and maybe a half here is useful. Now there's no harmonic term, so it's just the commutator, xi, xj, between all pairs, sum over I and j. And there is a fermionic term with some other gamma matrices. It's exactly the same, but now the gamma matrices are 16 by 16, sorry, psi. Okay, so these are 16 by 16 dimensional gamma matrices of SO9. So this model has SO9 global symmetry. And also SUN, of course. Okay, so that's what BFSS is. And BMN is a deformation where you add harmonic potential. So you take this model, which is pure interaction. There is only quartic and Yukawa-like interaction. And now you add to it a specific, okay, maybe I should have written this before, xi square. The funny thing about this deformation is that it breaks SO9. Okay, to preserve supersymmetry, you have to break SO9. So that's some. So you have to give different masses to the first 3 matrices. Sorry, I from 1 to 3, then to the next 6. And then there is another mass to the fermions, so a quadratic term to the fermions, gamma 1, 2, 3 psi. And finally, there is a cubic term. So these are all fixed by supersymmetry, xi, xj, xk, epsilon I, jk. Okay, so yeah, now the only thing I wanted to say is that this one is SO9 symmetric, and this one, BMN, is SO3 cross SO6, and both of them are SUN, of course. And what's interesting about these models? Well, first of all, some basic facts. So BFSS is a model with a continuous spectrum, while BMN as a discrete spectrum is like putting the first system on a trap. But the continuous spectrum of BMN, of BFSS, is particularly interesting because you have a ground state at 0 energy, and then you have some continuous starting from 0. So these are scattering states. And here you have a unique normalizable ground state. Normalizable ground state. Okay? While here you think of it as an harmonic trap, so you have some discrete energy spectrum. Okay. Any question about the models? Okay, so these are the definitions. I go now, I consider my job done. I give the Hamiltonian to Giuseppe. But now he will ask me, what should I do? What can I measure? What do you want to know about this Hamiltonian? Right? So that's my next slide. What do I like to know?
Joao, sorry, can I ask you,
Yes.
you commented before that in the bosonic model, even with the commutator, you had a discrete spectrum. Can you comment on why this is continuous instead? Or
It's
why
because of the fermions. It's non-trivial.
Okay.
So if you look at it classically, again, commuting matrices don't see a potential. So it looks like you can send the particles infinitely far away without energy costs. So usually you would expect a continuous spectrum. It turns out that if you don't have the fermions, so if you remove the fermions, these valleys are too thin, so the transverse directions get compressed, and effectively there is like the ground state energy, the 0-point energy of the transverse oscillators lifts the valleys quantum mechanically. But with the fermions, the ground state energy from the fermions is negative, so it cancels. So even the quantum mechanically, these valleys are really there, and the spectrum is continuous. It's non-trivial. Okay, so what do I want to know? So ground state, I want to know, it's very complicated in BFSS. Nobody knows what the ground state is. We know it has exactly 0 energy for supersymmetry, and it's unique. But for example, nobody knows even simple things like what is the variance, like the size of the ground states. We don't know, okay? As a function of n. Not even for n equals 2, we have a good handle on that. But then what is really, really useful is scattering amplitudes. This, Giuseppe, I don't know if there is any method that computes scattering amplitudes in quantum mechanics. Here, that's like the most important observable for BFSS to some extent. And you think about it like that. So you take your matrices and you look at the diagonal. Okay, and you put the diagonal in a vector. So x I equal 1, x I equals 2, and you make a 9-dimensional vector, right? So this is a vector in R9, sorry, R9, and it's yeah, there are n vectors of this. I runs from 1 to n along the diagonal. So you think of that as coordinates of particles in R9. So each particle, you have n particles. These are coordinates. And when they are very far away, they don't see a potential. This is what I just explained to Marco, n particles. And so you can prepare incoming wave packets and see how it scatters. Okay. These scattering amplitudes in quantum mechanics, these scattering amplitudes give graviton scattering amplitudes in string theory. Okay, so that's how this string theory map works. So if we knew these scattering amplitudes for any n and we took the appropriate large n limit, we would actually learn how gravitons scatter. In particular, they can form black holes, black hole production. All the richness of graviton scattering is in these quantum mechanical scattering amplitudes, if we knew them. Okay? And finally, the last thing that would be very interesting to know is finite temperature, because if you put the system at finite temperature, there is a metastable state. Okay, so of course, there is a flat direction because particles can just go away. But at large n, there is a metastable state, which is very long-lived at large n. And this metastable state is again, well, maybe I put it again in green. On the string theory description, this is the same as a black hole. And it decays because a black hole in this theory can decay by emitting Hawking radiation. Okay, so all this physics is in this quantum mechanical system. And now I guess I have 5 minutes. Yeah, it's good. I think I'm good. Any question about this? Okay, so ground state seems to be more closely related. Finite temperature, maybe Giuseppe can tell us. Scattering amps, I don't know if people thought. But if you want to be more conservative, then you can do BMN, because BMN is really a discrete energy spectrum. So it's like putting the previous system in an harmonic trap. And so if we can compute the energy spectrum, we can in principle extract also information about gravitational physics. Okay, it's kind of a regularization. It's like when you do statistical mechanics, you put a gas in a box because that's the way you get it to equilibrate. Okay? And that's what I have here in below. So you can actually define a phase diagram if you put this system in a box at finite temperature. So the box is this mass parameter mu. And we expect, so we actually know here, when mu goes to infinity, we have an exact solution. It becomes basically just harmonic oscillators. And we know that there should be some curve like that, which is a large n phase transition. So this is quantum mechanics, so there's no phase transitions. But when n goes to infinity, you can have a phase transition. So in particular, below this temperature, the energy, the expectation value of the energy scales like n to the 0, does not grow with n, even in different systems with different n, they are the same. While here, it goes like n squared, okay? So this is what we call the black hole phase. So if we also understand the thermodynamics of this system, we also get all this rich physics. Okay, and now I have 3 minutes to the last part. Any question? Now, for some of you, like myself, you already understood that quantum mechanics is too hard. So let's just do integrals, okay? If quantum mechanics is too hard, there's also an interesting question for you. We can just do statistical mechanics, okay? It's no quantum mechanics, just statistical mechanics. Think of particles in a gas, right? You just have positions and you have some distribution, equilibrium thermal distribution given by some energy function, right? That depends on the configuration space of the gas. So here, I organize my degrees of freedom into matrices, and now there are 10 instead of 9. There are 10. Is the price to pay to lose the time in quantum mechanics. And you just have to compute a partition function. Okay, so well, now I think I don't have time to write this. Maybe I'll jump. I'll show you, because otherwise I don't have time to write. The Hamiltonian is too long. It's here. Okay, let me erase too much information. Okay, so this is similar. It's some function of the axis, a trace. So there's a Gaussian part like before, and then there is a quartic part. So it's a difficult integral. It's a quartic integral. And the non-trivial part is this part here, which is a Pfaffian, okay, of a very large matrix. You can write it like that, or you can write it in terms of Fermion-Grassmann integrals, okay? I actually did the Grassmann integral and gave it like that. And this is also hard because this Pfaffian is complicated, so it comes from this Grassmann integral. And worse than that, it's not positive. So that's why we have a sign problem if we just want to do Monte Carlo for this statistical physics system. But perhaps the similar methods that you can use for quantum mechanics can be used to somehow control this measure where, well, it's not a strict measure in the sense it's not positive, but do this integral in a smart way, okay? And again, well, I give you here. So again, one target will be the size. We don't know the size as you move some parameter. So there's some gravitational prediction, but okay. This is perhaps too much for this now. So let me go back here and perhaps stop here. Thank you.
Thanks, Joao. So are there any questions? So the idea was now to have discussion on the relative to the talks, and also a question that could arise from the talk. So maybe we can start directly with questions for Joao and what he was telling us before.
Sorry, Joao, how big is the Pfaffian again? So what's the dimension of the matrix?
It's also n squared.
It's not exponential, right? It's okay.
The matrix, the size of this matrix is not exponential. It's I erased it. Maybe I should.
Yeah, okay.
16n squared times.
So it's computable. I mean, you don't need to do anything weird. Okay.
Yeah.
I mean, the Pfaffian of that matrix can be computed. It's fine.
Yes, for reasonable n, yes, but it will, yes.
Yeah,
it's hard to write explicitly,
scaling is like
analytically, but yeah, in a computer it can be, yes, true. Yes.
So the main problem is that you have a complex S.
It's
well,
no, S is actually real, right? So here you see this I, but that's okay because this is antisymmetric. So if you take, this is actually the trace of an Hermitian matrices. No, the action is real. This part is completely good Boltzmann weight. It's just the Pfaffian that doesn't have well-defined sign as plus or minus.
But this is not a problem.
Well, no, this model is recent. It was written down maybe 20 years ago, but nobody noticed it. We started to look at this model last year. So yeah, there might be some.
No, what I want to say is that maybe you can just do Monte Carlo on this, but okay, we have to talk.
Maybe you're saying that the fact that this sign changes might not be a very bad side problem, that maybe some reweighting would be okay.
Well, yeah, I mean, I think you can still compute.
You mean I take this as the measure, and then I take it, and that this is the average of.
Yeah, okay, but it's true that okay, no, sorry.
It's not clear if.
Yeah, no. It's it might be still bad. No, okay, but no, sorry. No.
because if you think about
But we can learn it. There are ways maybe to learn it, yeah, with a neural network.
So, sorry, can I ask why did you guys stop? So it looked, why can I take P to be just an operator and then I'm
you
just
can.
computing?
We did not do it. I mean, we didn't.
No, not doing the sense of not doing, but you guys stopped, meaning you seem to be not very optimistic at the end. But if you can compute P of X for each configuration, can't you just
For
do an
me,
average?
I'm not optimistic because P comes from a Grassmann integral, which also has order n square variables. So I don't think it's in any sense smaller than S. So it's like trying to average it with the wrong distribution. So it's gonna be P deforms the distribution as much as this essentially. I mean, to the n scaling at least.
Okay, I see.
If for
Good.
can I ask a question? Yeah, for particular values of n, what is that you would like from the Pfaffian to recast it as some kind of effective action for x, and that structure is kind of difficult to see, or
For fixed values of n, the Pfaffian is essentially like a polynomial in x and products of x and traces, and but the degree grows with n. I guess grows with n squared. Yeah, right. Yes.
Can I ask?
cannot make any argument say that the x's are you cannot make any argument some like effective action that the x's maybe are small because e to the s is gonna be minimal somewhere, right?
Well,
But
I mean,
okay.
you can certainly take limits. So you have this parameter omega. So for example, when omega is large, this model becomes easy because you kind of become mostly Gaussian. But when omega is small, then well, if omega is also very, very, very small, you can also do an expansion. I showed you here, right? The most difficult regime is when n is large and then omega is in this window that you have this gravitational prediction. And so we have some prediction from gravity and from supersymmetric localization for some specific combination. But for example, if it's not exactly this combination, then we already don't know exactly. We don't know. Yeah, localization doesn't work for example.
I see. Thanks.
Can I ask a question?
Sure.
Can you hear me? First of all, I'm sorry for interrupting Francesco. Can you go back to the phase diagram and the discussion on? This is a naive question. I don't know much about matrix quantum mechanics, but can you discuss the difference in the thermodynamics of the black holes in the different theories? Because here in BMN, you have this, you show a phase transition, so a discrete spectrum, so it kind of behaves like a Hawking page phase transition. I'm thinking like, okay, it's a black hole kind of in ADS or something related. But then in BFSS, in the previous slide, you said it was a continuous spectrum and a metastable, so the black hole would evaporate. So can I think of the introduction of the quadratic term, the harmonic term, as generating these different geometries, like a flat space geometry where the black hole does evaporate, and in the other case, like a boundary term that introduces back reaction and a positive heat capacity of the black hole? Can I?
Yes, it's exactly that. So in BMN, the harmonic potential corresponds to make the spectrum discrete, and it means that you cannot go to infinity, right? It's like you're trapped inside this harmonic trap. And therefore, if you start to eat up the system, you form this black hole. And now this black hole can be in equilibrium with the radiation that cannot escape from the trap. Yeah, exactly. It's exactly that physics. But it has to be big enough to be irradiated. So that's why there's a finite critical temperature. You see,
Yeah.
the black hole only appears if the temperature is big enough, so that then it can be in equilibrium. In BFSS, you don't have this harmonic trap, so you can lose radiation to infinity. And so the black hole is just metastable, and then it slowly decays.
Evaporates. Yeah. Yeah. Makes sense. Thank you.
It's exactly what you're saying.
Maybe I could ask, just a curiosity, is there any interesting information in the excited states of this model?
Yes, there is a lot. Well, one answer to that question is that we can at least compare to predictions in the gravitational side, because we have some geometries that correspond, say, to the vacuum. So in this model, actually, so I'm not being very careful here, but there is zero energy states. There's a degeneracy, so there are degenerate ground states. But we have dual geometries to each one of them. And so one can also, in principle, study the excited states on top of these geometries, right? By studying fluctuations of the metric and other fields. So kind of and all these geometries also have a discrete spectrum of oscillations because they are of the same type, like traps. So one can compare then those excited states with the excited states directly from quantum mechanics. So that would be already a more non-trivial test going beyond the ground states for which we know the geometry. And then we could even try to be more ambitious, right? Because in ADS, for example, we know that if we know the discrete spectrum very precisely, we can also take the flat space limit and get the scattering. So there should be something similar here, right? If you know the discrete spectrum very precisely in the harmonic trap, you can take a limit and get scattering without a trap. So, for example, you could also do that.
Okay, thank you. And just what you were talking, the few maybe to the last slide. I don't know if it's. I didn't get if the problem was computing P of X or
No, the
so
problem
is it sampling or
compute the partition function averages of this X.
Okay.
X is some configuration space of the system, so it's 10 matrices, okay, so many, and you want to compute, say, the expectation value of X squared or X cubed, things like that, and to understand the thermal averages in this ensemble. And the problem is that it's very big, so you need to have an efficient way, like Monte Carlo, of doing that. But since this is not positive,
okay.
Yeah.
Okay. Thank you.
I mean, in principle, you could just do the integrals, but the integrals are not Gaussian, they are quartic, and they are 10 n square integrals, right? So that's it.
So João, and then what is the relation between this model and the previous ones?
Well, this relation, yeah, this one is obtained from d instantons, right? So they're just zero-dimensional, taking the decoupling limit on d instantons, and BFSS is taking the decoupling limit on d zero branes. And then, okay, this you just get BFSS or the IKKT. Okay, the polarized just means that you have this mass deformation, this omega. Then to have this omega or the mass in BMN, it's a bit more subtle. You kind of have to take this decoupling limit in a non-trivial background with some flux in string theory. Was this kind of relation you're looking for, or
Yeah, in the end, they are describing the same physics, right? In the bulk.
Yeah, like n equals 4 super Mills, yeah, or ABJM. It's true. These are just going down in dimension. Yeah. Yeah, I could have spoken here about n equals 4 super Mills, but then the methods of Giuseppe, I think, are not ready for that yet.
I think one peculiarity of this system is the interactions with the commutator square. That may be something that in spin system is not usually seen, right? Because
Yeah,
even
I agree.
even for small n, I don't know, maybe you know, Joao, use the literature. Even for small n equal 2, there is no mapping between this Hamiltonian and some spin system Hamiltonians, right? Or am I?
Not that I know of, but you see, let's think about that for a second. So for small n equals 2, right? So you have 2 by 2 matrices, and you can remove the trace. Okay, here I didn't remove the trace, but the trace is decoupled. So you can remove the trace. So essentially you have 3 components in each matrix. So you have 3 times 9, so you have 27 bosons. So that's already the starting point, is 27 bosons. And then you have this 16 Majorana, and again you can remove the trace, so it's 3 in the 2 by 2 matrix. But so it's instead of 8 times 4, you have 8 times 3, so you have 24 spins. So it's already a pretty rich system. It's 24 spin a halves, 24, 2 to the 24 the fermionic, coupled to 27 bosons. So yeah, I don't think this is the kind of models that you find in condensed matter or spin systems. Maybe more like molecules. I don't know if you can think of these bosons at positions of the molecules and then some.
No, in cavity systems, yeah, there are similar things.
Sorry?
Where you have a sort of cavity,
Cavity.
quantum. But yeah, so you have the modes of the electromagnetic field and there are a couple too. Yeah, so you have molecules in a cavity. These are
And yeah, so that, and then you're right. Also, this commutator square, it couples almost everything to everything. Yeah, it's very. It's not like spin systems with short range interactions. It's very. There's lots of interactions with all the degrees of freedom. It's in a way long range. So those are the peculiarities, but I don't think it's really makes it impossible. Just for n equals 2. I just don't think nobody really tried hard enough to solve even the n equals 2 case.
I see. But a related question even for Giuseppe, are there any applications of machine learning to the eigenstate thermalization? Because I think possible questions that Joao mentioned about this model are related to black hole physics in some bulk string dual, but in practice what it means here is just that you're looking at the states which are under a distribution, and the typical state is essentially random in this XOR in this bosonic or fermionic variables. So I was wondering whether.
So you want to see the dynamics of this, sorry, or so thermalization? Sorry, what do you mean? Like the dynamics at long times, or the?
Yeah, I mean
the Boltzmann.
So the dynamic Salon times for observable should saturate to some value that is universally given by some effective temperature.
Right,
So I was
yeah.
wondering whether you can have that out
Yeah.
of studying an Hamiltonian in the case in which you don't focus yourself or restrict yourself to the ground state, but you look to some excited states, and then you study the statistics, because if you have an excited states, then you take a distribution of those, and then you see what happens.
Yeah, no, typically we do the dynamics and see because computationally it's easier to just follow one state rather than compute all the spectrum. Yeah. But okay, but I think that for this model, yeah, already the n equal 2 is quite rich, as Joao is saying. So I think one could start from there. Yeah, it should be it's interesting. Yeah. And using these ideas that I was mentioning briefly before of the backflow transformations, one could easily come up with a starting point, which is the non-interacting state, maybe, and then try to introduce a coordinate or transformation that makes it interacting. So this is something that we could try. Yeah.
And in that way, you preserve, say, these symmetries exactly, the SUN and the SO3, SO6 or something.
Sorry, what?
You would preserve exactly the symmetries.
Yeah, I mean, by construction, since you backflow, so I mean, you input modified coordinates inside the non-interacting state. If the non-interacting state has the correct symmetries, and if your transformation, of course, is equivariant under this transformation, then it's easy to do spectroscopy even of all the levels that you need. So if you want, then you shift the question into crafting a transformation that does not change the symmetry. But these are much easier to do than typically. Yeah, and then the other thing, I think, you might need to introduce some basis for the bosons, some Fock space there, and okay, I don't know which one is the most natural. I guess the harmonic oscillator. I don't know what to use. I guess it's the same you use when you do Hamiltonian truncation. No?
Yes, we use that. Yeah. Although we had to use the width of the oscillator as a variational parameter, we could not use just the free one as.
Okay.
Because otherwise it would converge too slowly.
Yeah, you just need a complete basis, and then, I mean, it doesn't matter if it's optimal or not. Typical.
I had a quick question for Joao, if I can.
Sure.
So I remember there are these kind of bootstrap type constraints for these quantum mechanics models that people studied, where you basically you look at moments of look at the moments of the state, like like you had x squared or higher moments of the state, and then you find some recursive relation amongst the moments, which is basically the Schrödinger equation, I guess.
Yeah.
Then you demand positivity of some matrix of moments. Do these methods have any applicability in the models that you're looking at? Or?
Yes. So for BFSS, I guess the state of the art is Henry Lin and Zexuan Zheng, and so they studied. The latest paper is about the ground state. So they actually use the fact that it's supersymmetric. So they use also that it's annihilated by Q to generate these relations between the moments.
Mm-hmm.
And I mean, it's very impressive. They still don't have an island, but they have a very sharp peninsula where in the space of these moments, trace x squared, and I think trace x to the 4, something like that, where they think the actual true moments live.
Does this depend on n? Do you have to take small n to do this, or does it not care?
No, they can do several n. Yeah, they can do n is a parameter. It's easy to. The problem there is that you basically have one shot because you take a set of moments like products of x's, trace of products of x up to some length, x, p's and psi's up to some length. And this thing, of course, grows exponentially in the length, right? Because it's the ways of distributing x's and p's and psi's. So they went up to some length with great efforts and tricks of gamma matrix technology and all that. And they already got good results. And I think they might hope to go one level up, but that's it. Then it just gets prohibitively hard to do numerically. So it's very nice. One should try it, compare it. But again, if you really want to be very precise and improve systematically, you again will face this explosion of exponential number of operators and constraints. Well, it's not inconceivable that one has some smart idea of what operators matter more, and then when you grow, you don't take them all, and maybe, I mean, it's definitely worth exploring. Sorry, and another thing they did, or at least Erilyn did, I don't know if Zhenshuang was involved in that one, was finite temperature. So they did the same analysis at finite temperature, and that was directly in the large n limit, so that the metastability doesn't matter. It's effectively stable at infinite n. And so they can also get bounds on averages of several things, traces of x squared, stuff like that, at finite temperature in this metastable state, this black hole state. But similar comments apply. That okay, they did something, they got some nice bounds, but it's hard to improve systematically.
Great, thank you.
Thanks. Yeah, I apologize for the lack of references. So thanks, James, for this question that helped me cover a little hole. But yeah, there's many more holes. I really was just trying to transmit what kind of ingredients go into these models. But yeah, there's a lot of work on these models that I didn't mention.
So Joao, but so you now you're proposing to try n equal to 2 and try to do the numerics, but like what do you think is going to be conceivable like as a maximal n where you can push this numerically?
I don't know. This is really beyond my expertise. I'm just saying that from what I saw in Giuseppe's talk, it looks like this kind of methods are so general that these Hamiltonians should be tried. Now, if you can do a plot of, say, the energy or the moments as a function of n, 2, 3, 4, 10, and then extrapolate to n equals infinity or not, I don't know really what is possible and what's not possible. Yeah, I don't know.
We can be optimistic. We can do...
No, indeed.
Yeah.
Why not?
It's hard to say. But yeah. Yeah, I mean, for spin 1/2, we can do up to, I don't know, maybe 400, 1,000 spins. So here you have the equivalent. Yeah, I don't know. It's a bit different setting, but yeah.
Okay, so we can be optimistic.
But I mean, my real hope, to be honest, I don't know if actually maybe I can put it as a question to Giuseppe. Suppose you're giving a model like this, you want to solve this, but really we don't want to solve, because even if you give me the exact wave function, I will look at it like, okay, and so what, right? It's just too much information. what we would like is to see some pattern, some idea. What this wave function is trying to do is that. And then maybe from that idea, we see how it connects more with gravity, how gravity emerges. Okay, because here, you can just say, it's strongly coupled, so there's nothing we can do. But it's not generically strongly coupled, because generically strongly coupled systems are not described by gravitational systems in the classical regime. So there is some specificity of this type of strongly interacting systems that lead to emergent gravitational descriptions. But we don't know what it is. I mean, we know that usually involves matrices and commutators, but we don't really know intuitively what is happening. So the hope would be that if we get more information about exact wave functions, maybe we could learn that. But of course, this is much more speculative because I don't know an algorithm to get.
But I mean, what you can reasonably expect is observables.
Yeah, right.
Then interpreting the wave function is not a reasonable expectation. I mean,
so for example, is there any example where having a better wave function with artificial networks then led to someone getting a better ansatz, more informed, that then gives almost as good and it's more analytic?
no.
Yet. Okay.
No, but I mean, I think that in this case, the main interest is also computing the observables, not because that's the well.
Yeah, in a way, yes. But the observables that are really interesting are probably really, I mean, I don't think we'll ever be able to compute 2-to-2 graviton scattering amplitude in sufficiently high energies that it forms a black hole, and then this is like too. Anyway, I should be optimistic. Good, be optimistic.
So you're thinking like maybe there's a way to approximate the wave function, let's say, as there was, let's say, metric product state is one type of approximation, but maybe there's a better one for gravity, something on this line. And if you have that written down, maybe you can try to guess it.
Yeah, for example, we could speculate something like that. Yeah.
Okay.
May I? Francesco?
Sure.
Yes, go ahead. No problem.
So, okay, let me show up. You can see me now. Okay, I'm Ignacio. I'm well on the other side of the group of the project. Say I'm a person coming from QCD and looking at magnetic field theories and so on. So I try to connect a bit with what you are saying here and how all these methods can be also used in. So from our side of the project, and probably someone will speak about this at some point. And what I find difficult here for us is that I don't see observables, in the sense that on the QCD side, we know, or we try to estimate a series of observables and eventually correlations among observables, which give us information about the quantum states. And so the question here is, what are the interesting observables according to you? These observables can be, except at least they can be physical in the sense that they can be measured, or can be more hypothetical. You know, we can have a black hole scattering, still something which we cannot have in a lab, but probably okay. We can make some calculation about this. And what we find on the other side, on the physical side, there are observables which have the same form as some kind of operators which appears in gravitation, but of course, when we see them in QCD, they have a different behavior. The regime is totally different, but still is interesting to measure or to see how they behave even in a completely different energy regime. So yeah, probably this slide helps me a bit. Can you comment? Oh, no. You can comment about this.
Yeah, sure. No, I mean we have observed. There's lots of observables, like I said, moments in the ground state, like here on the. Can you see my cursor? No, you cannot see my cursor. You see it here. Sorry. Moments in the ground state, like here, or then this scattering amplitude. So as I said, you can think of this. You can prepare the initial state as a scattering state of n particles in R9 and then evolve in time and see what is the out state. Yeah. So this, or the thermodynamics, as I said, you put the system at finite temperature. Maybe, okay, if you don't like this metastable state, then you can work in this model, BMN, where then it's stable. It's really this phase. You want to understand the phase diagram here when the temperature is sufficiently high, for example. So there are many concrete observables that can be asked about these models. Yeah. And that can be compared to gravitational predictions. I mean, for example, the critical temperature in this region is predicted by a black hole we constructed 10 years ago. And there's no, now there are some, this one has been to some extent matched by Monte Carlo simulations. So here, the sign problem for this quantum mechanical system is not too bad. So basically, people can do Monte Carlo simulation with the modulus of the Boltzmann weight, and then they reweight the phase, and the phase doesn't oscillate too much, so the reweighting actually works. That's what was observed by initially by Anada and collaborators, and now other groups have confirmed this. I don't know. Does this answer your question, or you have something?
I was thinking in that direction. I was thinking probably have to deepen a bit. So, I know there are some groups that try to apply what are effective field theories, which have more acute origin to gravitation, and they come up with some observables, which are, I don't know, yeah, scattering of galaxies and then make correction and so on, and which are probably, doesn't matter they're real or not real situations, but and then they have a configuration which is very similar to, yes, spin configurations that you are showing here. And I don't know if you were working also on these or not. Seems not, but they. Okay, never mind. Thank you.
Can I ask about this metastable black hole? Is there a way, at least in principle, it's probably very complicated, but is there would there be an observable, like a way to construct a state which looks like a black hole, which is somehow localized in space-time, this R9, and then compute some partial trace and compute some von Neumann entropy as a function of time? One constructs the states, evolves, and then wants to see if the entropy goes up and down like it should.
Sorry, I'm not for. What's your intuition that the entropy goes up and down?
I'm just thinking about the evaporation of this black hole and the page curve.
Ah, the entropy between, I see, between the radiation and the.
Yeah, so tracing in Hilbert space adapted with the coordinate x. So like it would be a state in which the x for large, like at large x, there's no energy density.
Yes.
And then one takes some cutoff and traces over. I'm not sure what I'm saying, but I mean the
Yeah,
gravitation intuition should be that.
So yeah, I think so. Sean Hartnell has been doing some work in entanglement entropies in quantum mechanics, like this one. You have to the target space X, you split. Right, it's not like in quantum field theory where you just split your original space where the fields live. Here it's the target space that you need to split. I think there's also some, the original work is like Sumit Das and collaborators. So there are ideas of how to do that, to project the state where all particles are outside some big ball or inside some ball, and do the entanglement in real space, in target space, like you are suggesting. Yes, because indeed the black hole here will be localized, I mean, around the center of mass, and then these particles, when they radiate, they go to infinity. Yeah, I think in principle it's contained in this model. Probably hard observable, but it's here.
Because there's still a lot of discussion in this business about whether even the page curve does actually go down in a model which has massless gravitons. That's really physics,
Well,
which is not
here it's a bit
understood.
subtle, because here there's no massless gravitons. Here it's an evaporation into D0 branes. So here it's an extremal black hole. Sorry, I'm saying it's not. It's a charged black hole. And the charge is this n, the number of D0 branes. And it can only evaporate by emitting charged objects. And so they just lose one D brane at a time. So that's also why it's so long-lived. It's because the decay rate is exponential. It has to emit at least one D brane. One particle, one of these D0 branes are these particles. So it's not exactly the same intuition as Schwarzschild in flat space-time.
Okay.
But for entanglement, this would be similar. Yeah, I think so.
Sorry, I will need to go soon. Sorry about that.
We need to go soon. Indeed, we have another meeting. Yes.
Yeah.
Yes, there was a cutoff today. Yeah. Okay, if there are, we can continue the questions eventually for another session on Thursday and Friday. But so for the moment, let me thank a lot Giuseppe and Joao for the presentations. Very interesting. And we hope to come back soon on these problems. So have a nice afternoon. Thanks.
Thank you. Bye-bye.
Everyone.
Thank you.